All right, welcome to the deep dive. Today, we're going way back. We're going to 2012 to explore the inner workings of the Android camera system.
Yeah, 2012. That's over a decade ago. Some people might say, why bother? So
Yeah,
much has changed. But, there are some really fundamental concepts in this presentation that are still relevant today.
you're right. Plus, it gives us an appreciation for just how much things have evolved. Like, we've got Exposing the Android Camera Stack, presented at the San Francisco Android User Group.
By Balwander Kaver and Joe Rickson from Aptina Imaging Corporation.
Right. And they really got into the weeds. So think of this as a guided tour of how your camera data actually gets from pressing that button to seeing the image on your screen.
And maybe even beyond, like what happens to that data. We'll look at apps, frameworks, hardware, the whole shebang.
Yeah, the whole stack. So let's start with like what you actually interact with as a user, the Android camera APIs. Back then, the core of it all was the Android.hardware camera class.
Yeah, think of it as the main hub. It handles things like opening and closing the camera connection.
But it's got a whole bunch of buddies, right?
Like a supporting cast, you've got things like camera info. This tells you basic stuff about the camera itself. Is it front-facing, rear-facing? What's its orientation?
Right. And then you've got camera parameters, which is where the real fun begins.
This is how you control all the camera's features. The presentation breaks it down into 3 groups. What's mandatory, optional, and custom.
So mandatory, that's got to be there, right? Things like getting the supported preview sizes, how big that little preview window is before you take the picture.
Exactly. Then there's optional stuff, like checking if the camera has video stabilization.
But this is where it gets interesting. Custom parameters. It's like this dumb piped, as they called it, for vendors to add their own special sauce.
Yeah, so all those unique camera modes you see on different phones, chances are they're using these custom parameters behind the scenes.
I see. And within those parameters, you have all the usual suspects, right? Auto white balance, different scene modes, focus modes.
You also control the preview image size, the actual photo resolution, even the thumbnail dimensions.
So much control. And then there's camera size, which is pretty obvious, width and height.
And then you've got camera.face. This one's for detecting faces in the frame.
It's not just finding them, it also gives you data, like the location of eyes, mouth, and a box outlining the face.
Right. And then camera.area, those define regions in the viewfinder, along with a weight.
Ah, so that's how you tell the camera where to focus, how to adjust the white balance, and set the exposure.
Exactly. Those areas basically tell the camera what parts of the scene are most important.
Nice. And all of this happens through a bunch of callback interfaces.
These are like little messengers letting your app know when something specific happens with the camera.
Like autofocus callback tells you, hey, focus is locked.
You've got air callback for when, well, something goes wrong.
Then there's face detection listener. You get the idea.
There's even one for zoom changes and picture callback. That one's important.
It gives you the actual image data, like a JPEG or RAW file.
And don't forget preview callback. That gives you access to the continuous stream of frames from the camera, even before you hit that shutter button.
Wow. So much going on behind the scenes.
Now, even back then, Android was evolving quickly. Jelly Bean 4.1 brought some cool new stuff to the camera API.
Oh yeah, Jelly Bean, what did it bring?
One big one was camera.autofocus move callback. This allowed developers to, track the autofocus adjustments in real time, both for photos and video.
So smoother autofocus, especially for video.
Exactly. It makes a huge difference when things are moving. They also added Android.media, media action sound that might seem minor.
But it was important for consistency.
Yeah. It let those apps with custom camera interfaces play the standard shutter sounds.
Yeah.
So it wouldn't sound totally different from the built-in camera app.
Right, and it wasn't just API changes. The camera app itself got a big redesign in Jelly Bean.
They split the codebase into 2. Package SAP's camera for the main app and Package SAP's legacy camera to support older devices.
But the cool part was this new swipe gesture. You could swipe left and instantly see all the photos you'd just taken.
Like a film strip. And you could do stuff right there.
Yeah.
Crop, rotate, share, delete.
Yeah, just like you could in the gallery.
And what's really neat is that the live preview kept running in the background. So you could jump right back into taking photos.
That's smart. So just for some context, let's rewind a bit to Ice Cream Sandwich Android 4.0. It also brought some cool features.
Oh yeah. 4.0 was big. It was the first with face detection and even face recognition built in.
And panoramic stitching. That was pretty impressive back then.
Right. And then you could grab a still image while recording video, they called it video snapshot, and separate controls for locking the auto exposure and white balance.
Wow. What else?
Continuous focus mode with region of interest control became standard.
So you could tap on a specific area and tell the camera to keep it in focus no matter what.
Exactly. Oh, and there was a lot of hype around zero shutter lag.
Ah, yeah, the dream.
But the presentation mentions it wasn't an API feature. It really depended on the camera hardware itself.
It still does.
True. And we got video stabilization officially at API level 15.
Oh, and live effects, right, for both photos and videos.
Yeah, you could use the Android.media effect framework to add all sorts of cool stuff.
All right, so with all these tools at their disposal, what were people actually doing with the camera?
Well, the presentation breaks it down into a few main use cases. First off, live preview. Yeah, that's what you see on the screen.
And apps could also get a copy of those preview frames, maybe do some processing.
Exactly. And then, of course, capturing photos and recording videos.
The bread and butter.
But there's also configuring camera settings, adjusting all those parameters.
Oh, yeah, and getting metadata, like those face detection details.
Right, and using the video snapshot feature. Then there are all those event callbacks.
The notifications.
Yeah, like when the shutter clicks or when focus is achieved.
Makes sense. And if a developer didn't want to build their own camera interface, they could just use Android intents.
Yeah, basically tell the system, hey, I want to take a picture, and let the default camera app handle it.
Nice and easy. Now, what about switching between taking photos and recording videos?
Good question. They outline a pretty specific sequence of steps.
Let's hear it.
First, you open the camera and start the preview, just like taking a photo.
Got it.
But then you have to call unlock on the camera object.
Unlock. What's that for?
It's like temporarily releasing control of the camera because the video recording is handled by a separate process.
Interesting. So you hand the camera over to the media recorder.
Exactly. Then you follow the usual media recorder steps to start and stop recording.
And when you're done?
You call reconnect on the camera object.
I see. That gives your app back control of the camera.
Right. Then you might restart the preview if you want to take more photos or videos. And finally, when you're done with the camera altogether, you call stop preview and then release.
So that other apps can use it. Okay, face detection. How did they implement that?
Well, first, you had to check if the hardware even supported it.
Makes sense. How'd you do that?
You'd use camera.parameters and a function called getMaximumDetectedFaces. If it returned a value greater than 0, you were good to go.
So then you'd call start face detection.
Yeah, and then the info about the detected faces, an array of face objects, would be sent back to your app.
Through the face detection listener.
Right. The on-face detection callback would give you all the details, like where the eyes, mouth, and bounding box are.
So you could do things like, draw a green square around each face in the preview?
Precisely. And some of those fancy image processing chips, the ISPs, could even draw those boxes directly on the screen at a hardware level.
Really? That's cool. So it wasn't just camera apps using the camera, right? What about other applications?
Oh, yeah, there were some creative uses, like ZXing, the open source barcode and QR code library.
Ah, yeah, I remember that.
They used camera.setandshot preview callback a lot. Grab a single frame, check for a barcode, and then stop. No need for continuous preview.
Smart. And then Honeycomb API level 11 brought something really interesting.
Camera.setPreview texture. That was a game changer.
Why? What did it do?
It allowed the camera stream to be processed without actually displaying it on the screen.
Interesting. Why would you want to do that?
It opened up possibilities for doing heavy image processing using the GPU, the graphics chip.
I see.
Like with OpenGL. You could use surfaceTexture.updateTextImage to update a texture with the latest camera frame and then manipulate it however you want it.
That's much faster than using the main CPU, right?
Exactly. And the presentation contrasts that with using the CPU. Setting up preview callbacks with set preview callback, that would give you the raw image data, typically in YUV format.
Which is what libraries like OpenCV often use.
Right, but it's less efficient.
They even mention a Google I/O 2011 video where you can see this in action. All right, so we've talked about how you, the user, and the app developer interact with the camera. Let's go deeper. What about the Android media framework?
Right, the guts of the system. They break it down into this high-level architecture. You've got your application.
There's that app you're using.
Yeah, and that interacts with the application framework.
Okay.
And that talks to the camera service.
And finally, the camera service talks to the camera HAL, the hardware abstraction layer.
Which is like the bridge to the actual hardware itself, the camera subsystem. That includes the camera device driver and the camera hardware.
So the HAL is basically the translator between the Android system and the physical camera.
Yeah, it takes those high-level requests and turns them into instructions the hardware can understand.
They also show a process view where you see multiple apps potentially interacting with the camera service.
Right, using binder IPC, inter-process communication, and how different parts of the system talk to each other.
And the camera service also talks to the kernel drivers for the front and back cameras.
Yeah, using system calls and interfaces like iSurface and Surface Slinger, which manages what you see on the screen.
So let's say you're using a camera app. What's happening under the hood?
Well, your app code is interacting with the camera.java class in the Android framework.
But Java doesn't talk directly to the hardware, does it?
Nope. It uses JNI, the Java native interface. Specifically, code in Android hardware camera.cpp.
Ah, JNI. That's the bridge between Java and lower-level code.
Exactly. And the JNI layer does a lot of important stuff. It sets up a persistent connection called JNI camera context. That's how it handles those callbacks we talked about earlier, going from the low-level code back to your Java app.
Makes sense. What else?
It also holds references to the Java camera, face, and area objects.
Ah, so it keeps track of them.
Yeah. And if your app wants a copy of the preview image data, the actual copying happens in the JNI layer. It also allocates memory for storing those JPEG images you capture.
Wow. So JNI is a busy bee. All right, moving even further down, we get to the camera service. This is the big boss, right?
Yeah, it's the resource manager for the camera hardware.
It runs in the media server process.
Right, is libcameraservice.so. And it does a lot. It checks permissions.
Making sure apps are allowed to use the camera.
Exactly. It makes sure only one app is using a specific camera at a time. It directs those callbacks to the correct app. And it provides info about the cameras on the device, their capabilities, through camera info.
Really important stuff. Now, they also give a glimpse of the Android open source project structure, the AOSP for the camera in Ice Cream Sandwich 4.0, and some changes in Jelly Bean.
Right. In ICS, you had the Java framework code under framework-based car Java Android hardware. The JNI layer was in framework-based Korsney.
Got it.
The camera service was in framework-based service camera libcamera service.
And the interfaces, those iBinder definitions, were there too.
Yeah. And importantly, the camera HAL interface, the blueprint for how the camera service talks to the hardware, was defined in frameworks-based service camera libcamera service camera hardware interface.
And the vendor-specific implementation of the HAL, those were usually under hardware vendor camera.
Exactly. Now, in Jelly Bean, they moved some things around. The Java and JNI code stayed in the same place. But the camera service, the iBinder definitions, and the HAL interface definition, they all moved to framework SAV.
IOF. Probably stands for audio video. Makes sense.
Yeah. But the actual HAL implementations, those custom ones from the phone makers, those usually stayed in hardware vendor camera.
So speaking of the camera HAL, the hardware abstraction layer, this is where the magic happens, right?
It's the translator between the Android system and the specific hardware in your phone.
And it's typically written by the chipset vendors like Qualcomm or MediaTek.
Right. It takes those general commands from the camera service and turns them into instructions that the camera driver understands.
And they mentioned that older versions of Android, like Froyo, used a file called camera hardware interface.h for this.
Yeah, but Ice Cream Sandwich and later used camera.h.
And this low-level interface in the HAL talks directly to the kernel-level driver.
Using various methods, like v4l2, video for Linux 2, or sometimes OpenMax.
And they use standard file operations plus IOCTLs.
Those are input-output control commands, basically low-level instructions sent directly to the hardware.
Cool. They even provide a sample diagram of a camera HAL. It's got a memory manager for handling the image data.
Right, the camera driver interface.
Yeah.
A display surface manager for the preview in video.
An event notification manager for those callbacks. And a camera manager that oversees everything.
Yeah. It's a whole ecosystem down there.
Let's talk about that live preview. What happens when an app calls start preview?
That triggers a whole chain of events in the HAL and the driver.
And that preview keeps running until the app calls stop preview.
Exactly. And during that time, the app usually doesn't interact directly with the camera unless it's registered a preview callback.
To get those individual frames. Interesting. They even give us detailed flowcharts, sequence diagrams, showing how the preview starts up and operates with v4l2.
Yeah, in the startup sequence, you see the app calling start preview.
And that leads to the HAL making all sorts of IOCTL calls to the kernel driver.
Like video CSFMT to set the image format, video create UFs to request memory buffers, video CQBUF to queue them up.
And finally, video stream-in to start the flow of images.
Right. And then the operation diagram shows the driver signaling when a frame is ready.
The HAL takes the filled buffer off the queue with video CDQBUF, potentially sends it to the display, and maybe makes a copy for the app.
And then puts the buffer back in the queue with video CQBUF, ready for the next frame.
This brings up a good question. How does this constant stream of images sync up with the phone's display?
Yeah, the display refreshes at a fixed rate. It's a bit of a dance.
So what happens?
The HAL dequeues the frame from the V4L2 buffer queue.
Gets it ready.
Then it needs to get to the display subsystem. That might involve sharing the memory where the image is stored or copying it to a separate buffer.
And if the app has requested preview callbacks, the frame might be copied for the app as well.
Right. Once the display is shown the frame, the buffer goes back to the V4L2 queue.
Ready for the next image. Makes sense.
Hmm.
Now let's talk about the camera device driver. This is deep down in the kernel, right?
Yeah, this is the software that provides a standard API for talking to all sorts of different camera hardware.
And it has to handle a lot of different hardware configurations.
Absolutely. Whether you've got a separate image signal processor or if the image processing is done on the main system chip.
And V4L2 is commonly used for these drivers.
Yep. Though sometimes they use OpenMax.
And they even have a diagram of a typical V4L2 kernel driver.
It shows the main components. The V4L2 driver interface, the controlling interface, buffer memory management, and camera HW management.
And that camera HW management block handles each camera on the device.
Right. Detecting it, initializing it, managing power, starting and stopping the data flow.
So many things to keep track of. They also talk about how the Android Linux kernel itself handles cameras.
Like, it's designed to support many different types of cameras. The code for a specific camera is often in a single file.
And you can include support for different cameras at build time.
Yep. And a single driver might even support several different camera models.
But they mention that supporting more cameras can make the phone take longer to boot up.
Yeah, makes sense. The driver also needs to figure out the hardware topology.
Like how everything's connected.
Right. And for multiple cameras, the V4L2 driver creates those device nodes, like DVideo 0 and DVideo 1, so apps can access each camera.
That makes sense. Now, when it comes to resources, the driver has to manage a bunch of things, like memory.
Yeah, that's where the image data is stored. It can be allocated by the driver or by the apps.
And the actual data transfer from the camera often uses DMA, direct memory access.
Right, that's done by the hardware to make things fast.
And then there are interrupts.
Those are signals from the camera to the processor, indicating events like a new frame being ready or autofocus being achieved.
Got it. What else?
Camera control. That often involves using I2C or SPI to talk to the camera's internal settings.
And then control signals, those are managed by the driver using GPIO pins.
Right, to control different aspects of the hardware. And of course, power management is crucial, especially on a mobile device.
Yeah, battery life is king. They talk about the driver's buffer management system too.
It can handle multiple memory buffers for preview photos, video, and they're usually organized in a circular queue.
So it's like a waiting line.
Exactly. The buffers are filled when streaming is called.
The HAL dequeues a full buffer, processes the data, and then enqueues it again.
But when stream off is called, everything stops and the buffers are released.
Nice and organized. They also go through a typical V4L2 preview sequence step by step.
Yeah, the startup involves a bunch of video C calls, those IOCTL commands, like video CS FMT to set the format, video QBUs to request buffers.
And video C stream-in to start the capture.
Right. The shutdown is simpler, mainly just video C stream off to stop things and release the buffers.
Got it. Now, there are a couple of other things they touch on, like the V4L2 media controller architecture.
That was an attempt to give apps more direct control over the image processing pipeline.
But it was mainly for open source hardware at the time.
Yeah. They also mentioned that companies were starting to move their proprietary image processing algorithms out of the kernel and into user space.
To protect their IP, I guess.
Right, and to avoid licensing issues with the open source kernel code.
And they even give the location of the driver source code in the Linux kernel for anyone who wants to dig in.
Kernel sources drivers media video.
Yeah.
All right, let's talk hardware. They break down the different types of camera sensors, raw or Bayer sensors, and smart or SoC sensors.
Raw sensors, those output minimally processed data, right?
Yeah, in the Bayer pattern. They need an image signal processor, either a separate chip or part of the main processor, to turn that raw data into a usable image.
And they have simpler controls, mainly focusing on exposure time and signal amplification.
Right. SoC sensors, on the other hand, have an integrated ISP right on the sensor chip.
So they output already processed images in formats like YUV, RGB, or even JPEG.
Exactly. And they tend to have more complex controls. The sensor itself can handle a lot of the image processing.
They give some specific examples too, like the MT9M M032 as a raw sensor and the MT9M 131 as a SoC sensor.
Both using electronic rolling shutter. Now, for the live preview, you often need a smaller image than what the sensor captures.
So how do they do that at the hardware level?
There are a few techniques. Skipping is just discarding some rows and columns of pixels. It's power efficient, but not the best quality.
What else?
Binning combines the charge from multiple pixels into one. Reduces the resolution, but can be good in low light.
And then there's scaling.
Yeah, that uses algorithms to resize the image. Generally gives the best quality.
So wrapping up, they offer a peek into the future, looking ahead from 2012.
On the software side, they highlight memory limitations in phones. High-resolution images and boost modes were pushing those limits.
Still are, in a way.
True. They also predict the rise of computer vision applications.
Things like object tracking and gesture recognition.
Right. And computational photography, giving developers more control over things like the flash to create better images using software.
That's become huge. What about hardware trends?
Backside illumination sensors were becoming a big deal. Flipping the sensor over improved light gathering.
Leading to better low-light performance.
Yeah, exactly. Smaller pixel sizes and sensor packages were another trend, and faster data output for high-resolution video.
Like 1080p at 60 frames per second?
Yeah. They also mention high dynamic range for capturing a wider range of brightness.
And 3D imaging with dual cameras, that's become pretty mainstream too.
It has. And that's basically it. They mentioned a Q&A section and their references.
Okay, wow, that was a lot. But really interesting. We've gone from those first taps on your screen all the way down to the hardware itself.
Yeah, it's amazing how much complexity goes into something we take for granted, like taking a photo.
Right. And even though this presentation's from 2012, so much of it is still relevant today.
It really highlights the fundamental principles behind how cameras work.
So here's something to think about. They talk about trends like smaller pixels and computational photography. How do you think AI and machine learning have changed the game even more since then?
It's been transformative. Think about all the features we have now. Portrait mode, night sight, super resolution zoom. It's incredible.
Right. And it all builds on those same foundations we've talked about. The interaction between hardware and software, the image processing pipeline.
Exactly. And what's exciting is that we're still just scratching the surface. Who knows what amazing things cameras will be capable of in another 10 years?
Yeah, that's a good question.
I can't wait to find out.
Me too.